Okay, hello everyone. Let's go ahead and get started. In case you missed it, I did get the exams finished late last week. The grades have been posted. Regrades are now open, so if you take a look at your exam and you think a mistake happened, definitely happens all the time. Submit a regrade request. I am not going to accept any regrade requests after Friday, so please get your regrade requests in by the end of the day on Friday. I'm not even going to look at them until Friday probably, so submit your regrade requests by Friday, and I will then go through them sometime over the weekend or next week, early next week, and get back to you on those regrade requests. What else? Homework 4 is out, so hopefully you've taken a look at that, gotten started on it. Homework 3, if you still haven't submitted that yet, the last day for you to do so is by Wednesday, I believe. So do have a couple days left on that if you decide to turn in late. Otherwise, I think that's about it. Are there any questions about homework assignments or exam stuff before we hop into today's topic? Anything I can address with you all before we begin? All right, cool. Let's go ahead and get started then. Today we are talking about distributed databases. So the last couple weeks we talked about introducing parallelism into our databases using concepts of transactions and blocking. That's a big component of what I'm asking you to think about with homework 4. So we're going to kind of wrap up the discussion on parallelism and concurrency by talking about distributed databases. That's going to be our topic for both today and Wednesday this week. And so what do we mean when we talk about distributed databases? We're talking about multiple nodes connected by a network. So up until this point, all of our data has just been sitting in one place. It's been sitting in, it could be on your laptop, right? If you've been following along with some of the exercises we've been doing in class, could be on your laptop, could be on a server sitting in a room somewhere, right? But now I want to talk about the case where I've got multiple pieces of data separated by a network, not just on a single location. So the data on the nodes is logically related, meaning that the database, I don't have two separate databases that are talking to each other. I actually have one database that is split into pieces and then put onto multiple different locations. And what's becoming more and more common these days is that the nodes of our distributed database do not have to be homogeneous. What we mean by homogeneous means that we do not have to expect the access method to be the same across all of those nodes, meaning that one node might be a super beefy, heavy server that I spent thousands of dollars on. Another node might be some computer that's sitting in the back of a closet somewhere that's not nearly as powerful, right? One node might accept connections via a fancy UI app or a website, perhaps. Another node in the database system might accept query requests only from, SSHing into the server and passing the requests directly to the database, for example. Those are examples of heterogeneous systems, and those kinds of heterogeneous systems, heterogeneous access paths are becoming more and more common these days. But really the biggest thing that matters in terms of our distributed database performance is the network. The network matters a lot. So the topology of the network matters. That is, what nodes are connected to each other. So who can talk to who, right? As well as the proximity. How far apart are those nodes from each other? So if I have two nodes that are across the building from one another, that's going to be a lot faster than if I have two nodes that are across the country or across the world from each other. So these are the kinds of concepts that we need to think about now when we're talking about distributed databases. And so what I want to spend the first part of class today talking to you about is, why might we want to decide to distribute our databases? Sounds like a lot of work. And also, what is that work, right? We don't just need to speculate on what that work is. Let's talk about the additional work involved with distributing these databases. So some distributed database concepts that will be useful for us going forward. First, an idea of transparency. Transparency, the answer to this question whether or not our users need to be aware of the fact that a database is distributed, I think the fact that you all have interacted with large-scale websites, large-scale applications online has already shown that actually no, our users don't need to be aware of the fact that the database is distributed. Certainly large companies like the Googles and Facebooks of the world have many servers spread out across many different locations, not just in this country, but other countries as well. And when we go to Facebook or Google or Twitter or some other large company like that, we have no idea what server we're actually talking to. And it might change depending on, the time of day, how many people are currently on the website, right? It's managing all that stuff behind the scenes, but for us, it just looks like we're going to Google, right? Or we're going to Facebook, and we can't actually tell the difference. That's the idea of transparency. So how much do our users know about the fact that the database is distributed? The ultimate goal here is that they don't know anything. But there are different forms of transparency that we should be aware of as well. So location transparency is kind of what I was just describing. Do I know what server I'm talking to? Do I know where that server is or not? Naming transparency. So if I call something by a certain name in a database, since we're talking about databases, that could be like a table name or a column name, right? Does that name mean the same thing here as it does on the other nodes? Like if I'm talking about the students table on this server, is the other node in the distributed database going to know what I'm talking about when I say the students table? Or did that table name get shifted somehow when it moved to that other node, to that other site? Or does it not even exist? Is it not a thing at all? That's the concept of naming transparency. Replication transparency. So part of the reasons why, one of the reasons why we distribute our databases is for the purposes of replication, making copies of our data. I think the most obvious reason why is for backup purposes, right? But replication transparency refers to the fact of, do I know whether I'm talking to, do I know if that data has been copied? Do I know what copy of that data I am talking to currently? Like if there's 3 different copies in the world, does it matter which of the 3 replicas I'm talking to or not? Do I even need to know? Does it matter to me? That's the idea of replication transparency. And then fragmentation transparency is perhaps one of the most important ones up here. The idea of if I have my database split up into chunks. We're going to talk a lot more about fragmentation actually a little bit later on today. Do I know that half of this table is on this server and half is on this other server? Is that something that as a user I am aware of or not? So these are all kinds of questions that can illustrate how user-friendly your database may or may not be. And in some cases it may make sense for us to expose these to our users. If I'm working on database development projects, I might want to know what the replication strategy is. I might want to know what the naming strategy is. Okay. Another important concept to consider when talking about distributed databases is the concept of autonomy. So can a node operate independently of the other nodes? There's many ways that autonomy can come into play, such as design autonomy. So is the design of my database such that a node can operate without having to compare notes with another node in the system? If I have a table that's split in half across 2 different nodes, then that's going to lessen the design autonomy because I've got my schema split up across 2 different places. Communication autonomy is the idea of how much communication a node is willing to expose itself to in the database server. Is it willing to go out and ask other nodes for assistance if it needs to? Is it able to do that? Or is it going to try and solve everything that it can do internally without accessing the network and maybe even give up if it can't do that? That's the idea of communication autonomy. And then execution autonomy is sort of a combination of the two. Can I access the data? Can I perform the communications necessary to to execute those queries? Do I need to communicate to execute those queries, or can I just execute those queries in place where I'm at? These all go towards the degree of autonomy. And I guess I should mention too, like with transparency on the previous slide, having a database that's fully autonomous or a database that's not very autonomous at all is not necessarily a good thing or a bad thing. It's just a different place on the scale of possibilities, right? Like most things in computer science, there are trade-offs. There are pros and cons to having a fully autonomous system or a system that's not autonomous at all, right? And it's up to us as database designers to think about those trade-offs, think about those pros and cons, and make the appropriate choices for our needs. Yes, what's up? So design autonomy is the idea of whether or not the actual schema of the database is spread out across multiple places or not. Can I access the entire schema without having to ask somebody else, or do I need to? Are there parts of the database that aren't available to me that are on other nodes that I need to ask? A lot of times we're not going to have design autonomy because distributed database, part of the flexibility, part of the great usage of it is to be able to spread our data out and not have to keep it all in one place. That is one of the advantages of a distributed database. So we're going to sacrifice some of that autonomy, usually for the sake of performance, or actually for the next topic. I'm going to spend a little bit of time making sure that we understand the difference between these two terms, because these two terms come up a lot. A lot of times people think they mean the same thing. They don't. They actually have two very slightly subtly different meanings to each other, and they are important. You can see that the textbook definitions up here on the slide, right, of what reliability and availability are, but I think it's better to illustrate these concepts with examples of how we might talk about these in real life. So reliability stated as a probability that a system is running. In actuality, what we actually care, what we really care about in terms of reliability is how long do I expect this thing to be able to work before it stops working, right? Or a metric that we might use to measure reliability is something called mean time between failures. How long can this system go before it quits, before it fails? So a lot of hardware components are measured with this this metric, mean time between failures. Hard drives are one of the more common pieces of hardware that are measured with this metric. If you look deep in the details of hard drive specs, you'll see mean time between failures listed as a property. But it's not just limited to that. Servers, machines, and even software systems can be registered with mean time between failures as well. And the computation for that is kind of involved, since we often don't have actual data to go off of, right? Like I'm not just going to run, 1,000 hard drives and see how long it takes. By that point in time, I've already designed a better one, so that data is not useful to me anymore. So we do some speculation, we do some prediction. I'm not going to get into the details of that, but that's how we talk about reliability. Availability is the probability that a system is continuously available, which is a bit of a recursive definition. Think of it as a percentage. Over a period of time, what percentage do I expect this to be available? So you'll commonly see availability discussed if you are going to be renting a server or getting some hosting for your website, perhaps. You'll often see the rule of 5 nines is what they call it. If I tell you that you've got 99.999% availability, that means that if you register with my hosting service, your website will be up 99.999% of the time. That is the guarantee that they are making to you. Which, if you want that in more practical terms, means that over the course of a year, you would expect less than 5 minutes of downtime, right? 5 minutes of downtime for your website. So So that's how we measure those two metrics. Reliability is a bit more speculative, right? Mean time between failures is the average time that I expect, but it's not the actual time. So it could be less, it could be more. It's just kind of a guess. If I'm looking into the future, right? How long do I expect this to work before it's going to fail again? Of course, I want to maximize that. I want it to be as long as possible, but I have to prepare for the worst case where it might fail sooner than what I expect. I have to prepare for that case as well. Whereas availability is like, all right, how often do I expect over the course of time to have to pay attention to this system? How often am I going to expect to have to wake somebody up in the middle of the night to go fix my servers, right? Restart my servers, whatever the case may be. So slightly different ways of looking at the same kind of problem. How do we construct reliable systems? The answer to that is fault tolerance. I want to make sure that my system can handle any kinds of errors that are thrown at it. So for the case of a database, right? I want to make sure that it can survive if there are errors with some transactions. Somebody submits a bad query to me or a bad transaction to me. I want to make sure that it doesn't bring the whole database to a screeching halt, right? That's a very simple, kind of obvious answer. But there are other things that we need to pay attention to as well. Like, what if the power goes out? What if, some of the more catastrophic things, I suppose, are probably not reliable, like earthquakes and floods and things like that. But even people will even try to go to great lengths to minimize the impact of those things as well. Availability is a bit trickier. Availability is a bit trickier of a problem to solve. But one way that we solve availability is actually what we're talking about right now, which is distributing our data. And we'll talk about that in just a little bit. All right. So now that we've introduced some terms, let's talk about why we might want to do this, and then we'll take a look at what it actually looks like when we distribute our database, when we decided to distribute our data. So some advantages are flexibility, especially if I've got a lot of operations I'm trying to perform. I'm no longer restricted to having to do everything in one place. I can look around, right, and see who maybe is not doing too much right now, who doesn't have a lot on their queue, or I can maybe try to spread out the computations. I don't have to just do it all in one place. I can try to minimize the impact of a large operation by spreading it out across multiple nodes. Increased reliability and availability. So we were just talking about those two terms. Availability is increased by the act of replication, actually. If I have two copies of data in two different places, one system goes down for whatever reason, right? I still have the other one up. That data is still available. It's a classic way that availability is improved. And actually, that's what your web hosting services are going to do as well, right? They're going to copy your data into multiple spots so that if one spot goes down, you still got the other one to lean on. Performance will hopefully go up. Kind of related to the first idea, we can do multiple things in multiple places, so that's parallelism. That's a different kind of parallelism, but still parallelism that we can lean on now with a distributed database. And it also makes it easier for us to expand. If I have 10 nodes in my database, what's one more? If I have 100 nodes in my database, what's one more? It's not going to make as big of a difference. Making the jump from one node to two nodes, though, that's a big change. That's a lot of work. So, now that I've hopefully kind of sold you on why we are interested in distributed databases, let's talk about the additional work that's going to be required to make these databases function properly. First, we have to manage where that data is going to live. I have a big pool of data, and I know that I want that data to live in 3 different places. So where am I going to put it? Where am I going to put that data? How am I going to split it up? Am I going to split it up? Maybe I'm going to choose to take that big pool of data and make 3 copies of all of it, right? That's a question that we now have to answer. And we have to think about the implications of the decisions that we make. How do I process a query when the data that the query needs is maybe in different locations? So again, we're trying to provide transparency to our users, trying to make it so that a user can submit a query and not even realize that that query is taking place somewhere else, right? So how can I do that and still process the data effectively, make sure that it accesses the other sites if necessary, the other nodes if necessary, and gets the correct result? If I have copies, that requires a lot of management. Why? Why is replication, what's the additional overhead if we decide to make copies of our data? Yeah. They're all up to date. Consistency, right? Consistency is big. So I have to make sure if I have 2 copies of data, I have to make sure that if one changes, the other one also changes, right? So there's some extra overhead involved with managing those different copies. Transactions become a bit more difficult. Transactions become a bit more difficult because I might be operating those transactions in different places as well. Recovery, so if one node goes down, how do I bring that node back up without affecting the other nodes? Is that possible? And then also security. The nice thing about having all of our data in one place is that I only have to guard that one place. If I now start taking my data and putting it in multiple places, I now have to guard all of those places, right? I have to protect all of them. So those are some additional concerns now that we have to address when talking about distributed databases. And we're going to get through most of those today, hopefully. And whatever we don't get to today, we'll get through on Wednesday. So before we talk about data distribution, let's go through a couple of examples of what a distributed database actually looks like. For all of these examples, we can talk about the distributed databases as far as the degree of homogeneity and the degree of local autonomy, as well as how distributed it is. There's actually varying levels of distribution. I can have more or less distribution, right? So actually, I like to draw a little diagram to kind of show where we are and where we're going. I'll erase this. Okay, so if I have a graph with 3 axes on it, on this axis, this will be autonomy. This axis will be distribution. And then this axis will be heterogeneity. Did I spell that right? I don't know if I did or not. It's close enough. All right. Up until this point, we've been talking about what are centralized databases, right? We haven't called them that because, as far as we were concerned, that was the only kind of database that we were even bothering to talk about. There was no distinction to be made up until today. But we've been talking about centralized databases. All of my data is in one place. So on the distribution, on the scale of distribution, a centralized database has none, 0, no distribution, right? We can think about how much autonomy and heterogeneity it has, though. If I am the only game in town, I have the autonomy to do whatever the heck I want, right? Nobody's going to stop me. So, and then heterogeneity also is kind of a non-factor because it's just me. Everything is the same because it's just me and I'm the only one. So all of the databases that we've been talking about up until this point today have a very high degree of autonomy, but no distribution and no heterogeneity at all. We would call this a centralized database. Where we are going is to databases that have lots of distribution, or if we think about it in its most pure form, right? A purely distributed database means that no data is going to be shared across any of the nodes, right? So every node is going to have its own distinct set. That's a purely distributed database. And oftentimes, up until recent times, right, heterogeneity was not a particularly pressing concern. So we would have servers in various places. The access method would be the same. The hardware would be the same. And so a pure distributed database, right, would look something like this. A purely distributed database would have a very high level of distribution, but because there's no overlap between the data, very low degree of autonomy. If one node goes down, that's a big chunk of the database that I just no longer can have access to. Right? And so that leads us to the last kind of database that's worth talking about, which is the kind of the more modern implication of databases where I'm going to have some overlap. I'm going to have some replication. We've understood the need for that. That's necessary. If I have more replication, that doesn't just increase my availability, it also increases my autonomy, because now there's at least a chance that if a node crashes, the other nodes will be able to keep going. I can't maybe guarantee it necessarily, but I've increased the probability of that being true. And also in recent years, the idea of having all of our servers be the same, having all of our access paths be the same, has become a very outdated way of thinking about things. We want to be able to access our data in many different ways across many different systems. High degree of heterogeneity. So really what we're aiming for is something that's like, I almost hate to draw it because it's in 2D space on a 3D graph, but you know, it's like floating, right? Above the screen almost. We would call this a federated system. Or an even more extreme version of that might be a peer-to-peer system. Peer-to-peer database system. Perhaps. So we were here. We're going to talk about pure distributed data a little bit, but where we really want to go is something like this, a federated system. I think what's important to take away from this little exercise, though, is the idea that all distributed database systems, or even non-distributed database systems, can be characterized using these three metrics. And those metrics actually tell us a lot about the expected behavior and expected performance of those databases. I also think that while we're clearly having this discussion about distribution and why distribution is important, I'm not trying to say that the centralized databases are no longer useful to us, because they are. They certainly are useful to us. They're not going to go away. They're actually relatively simple to manage compared to distributed databases, which is a very attractive advantage of them. Much easier to secure, as I mentioned earlier, which is a very nice advantage to a centralized database. So there are certainly reasons to keep using centralized databases. Okay. Any questions so far before we take a look at architecture? All right, so next we're going to take a look at the architecture of distributed databases, how it compares to where we've been. Up at the top, this is actually an example of a centralized database. So when you see the top of the two examples, a centralized database that might have some remote access to it, but still centralized. So I'd say the clients are distributed. I've got distributed clients across the world, perhaps. But the data itself is only in one place. It's only at one of the sites. That is a true centralized database. What we have down here at the bottom is what I mean by a distributed database. I have data at every single one of the positions, every single one of the sites. And think about what that means. I can submit a query here to site 3, even though the data that query needs to run is over here at site 2. Or maybe it's not even just at site 2. Maybe it's at site 2 and site 1 and site 5, right? That's what we have to be able to deal with now. I have to be able to deal with a query that comes in at any one of these positions that's going to access data at any one of those positions. That's the direction that we're headed in. Yes? Yeah, of course.
For the federated one, is it supposed to be, is it on the distribution access, or is it just
Yeah.
autonomous and autonomous?
No, it's on all three. That's my my wonderful drawing skills are on display. It's meant to be meant to be on all three. So I don't know how to make that illustrate that fact. I can draw some dashes, right? That's making it worse. That's not helping. It's like floating out in three-dimensional space. Yeah. I should have used MATLAB or something. It would have been much more effective. Any other questions? All right. So let's talk then about how that affects our workflow. The fact that I've got data in multiple places. Let's talk about how that affects. Actually, before we get to the workflow, let's talk about how that affects our schema, the way that our database looks to the out. Yeah, question.
When you do like a bunch of different like actual data storage locations, do you like just store the data wherever like when someone like wants to store something, you just store it at whichever server they're interacting with, or do you like hash the data in some way to decide which servers can go to all these little.
Could be either, actually. We're going to talk about where data lives. That's a big part of distributed databases is where we decide to put the data and why, and then how do we manage that once we've made that decision. Usually the answer to that question is not going to be based on any technical requirements. It's going to be based more on usage requirements. I'm going to put this data here because I expect those people to use it more often than the people over here. Right? That's by far going to be the most effective way of placing it. Yeah, yeah. So how does our database look to the outside world? And actually, how does this change our internal view of the database as well? The schema is how the world sees our database. And so up here at the top, you can see that there is now one global schema that the outside world can see. But this is not, this global schema is very abstract. You see it's labeled as conceptual because it doesn't actually physically exist. The global schema makes it look as though there is one database that has these tables in it, right? And at a conceptual level, at an abstract level, that might be true. But physically, that is not true. Physically, I've got separated sites that each are responsible for their own piece of that global schema. So every site has its own local schema, which is also conceptual, because consider that each individual site needs to know what data it has as well as the data that the other sites have. So it is also still aware of the fact that some of these columns or some of these rows live somewhere else. And then underneath that, it's like, all right, here's the stuff that I actually have. Here is my actual internal schema that I know about. Does that make sense, the distinction between those two things? So we're actually putting up a front to the outside world that says, here's what the database looks like when the real picture is not quite that simple. Each database is responsible for its own segment of data. And there might be overlap, right? There might be overlapping pieces of these schema in different areas. That can happen. But what we're projecting to the outside world does not match what we're actually doing. And then when we make changes to the database, we have to understand that fact. Or when I'm retrieving data from the database, the users are submitting their queries based on this global conceptual schema. And so then it's up to us as the database management system to decide, all right, here's what they want. How do I actually break that up into chunks and make sure that the query gets sent to the right places, the places that have the actual data? And so the actual query process is going to change as well. If we look at the architecture of what happens to our queries now, you see there's this idea of global queries and transactions, and then local queries and transactions. So at the global level, our user's going to submit the query, and we're going to compile that query and try to optimize it on a global scale. That's actually a very important technique that we haven't talked about yet, and we're going to. It's not the same as optimizing queries like we talked about with the heuristic. That's still important, but that's not what we're doing. We're globally optimizing a query. When we're globally optimizing queries, we're worried about things like, how can I minimize the amount of data that I have to communicate across the network? Once we've optimized that query globally, then we'll fire up the transaction manager, which is sort of going to oversee, right, that query across all the sites. We'll talk about that a little bit later. And then once the query actually arrives at the individual sites, it's going to go through the process that we're used to thinking about. It's going to spawn a transaction locally. It's going to optimize that query locally using the heuristic that we talked about, execute that query locally. Once it's finished, it will take the results and ship it off. Ship that information off wherever it needs to go. The global transaction manager will then collect all of that data from all the different sites, stitch it back together into one cohesive unit if it needs to, and then present it to the user who made the request. So it's a bit more complicated. You can see that the process that we did before when we talked about centralized databases still exists. That's kind of what's happening on each individual site now. But we've got an additional layer of overhead that is happening on a global level. But actually, where does this global stuff where does that happen? It's got to happen somewhere, right? There's got to be some machine or some process that's involved with managing all of that global stuff. Where does that happen? We don't have a whole lot of options. It's happening at one of the servers. Which one? Maybe all of them. Maybe they're all accepting queries, right? They're all taking in requests, and they're all globally managing those requests. Or maybe to simplify things, we want all of our requests to go through a single location that's going to manage all of that. There are pros and cons. There are pros and cons to those different kinds of approaches that are worth thinking about when talking about distributed databases. All right, let's talk about what was just asked a few moments ago. Where should the data go? I've got a big pool of data. I've decided that I'm going to split it up into multiple locations. How should I decide what data goes where? First thing we're going to do is break things down into logical units. So if I'm going to split my data up, what makes sense as split points, right? That's kind of the question that I'm asking. How do I want to split this data up? And there's more than one right answer to this question. So one that I mentioned earlier was location. If I'm a big company, I'm tracking accounts across the country, it makes sense that if I have accounts for Chicago and New York and Los Angeles, that I'm going to keep that information in Chicago and New York and Los Angeles. Is it possible that somebody from New York's going to want to access an account in Chicago? Yeah, sure, but I can still accommodate for that fact. In the general case, I would expect that most of the time, if I'm in New York, I'm going to be accessing accounts that are in New York, right? Based out of New York. So location is one way that we often use to decide how to split data up. What are some other ways that you can think of that might be useful ways of splitting up our data? There are other common techniques. If I gave you a chunk of information and said, partition this out, what might you look for? What might you try to do? Yeah. By type of information. Okay, so can you give me an example or elaborate on that a little further?
Maybe you have a data set of students.
Mm-hmm. Sure, yeah. I think that makes perfect sense. Or maybe if I'm making stuff, right? I'm making some products and trying to sell those products. The actual information related to manufacturing the products might live at the manufacturing plants, right? The factories. The information related to selling those products might live at company headquarters where all the salespeople are, right? So I can separate it off by the type of data that we are looking at. Absolutely. Yeah. What else? Any other ideas? Yeah.
Like the size of the data?
The size of the data. So how could size help us decide how to split things up?
Well, maybe some data is like really huge, so then you store that in like a database that's really big, and some database might be smaller. So
Okay. So even just based on the resources that I have available, right? Yeah. I think that's definitely something that we need to consider, something that we need to keep in mind. When we're talking about, especially when we're talking about performance of our database. Absolutely. It is important to consider, though, that the more data I'm storing in one place, the closer I get to having a centralized database. But that's okay. I mean, again, maybe that's what we're after. Some other logical units that might make sense would be time. Time is a very common way of partitioning data. Very, very common. So maybe I am a bank or some other firm that tracks records across time, but I'm only required to keep certain records of a certain point, or maybe I only expect certain records to be relevant to me, and as they get older and older, I don't need them anymore. I'm gonna take those old records, I'm gonna ship them off. I'm gonna keep the new ones easily accessible to me. So I'll partition by time, perhaps. Another common way of thinking about things. There are many other ways to consider fragmenting our data, but those are some of the most common ones. And so once we've made the decision to spread our data out, to split it up, and what criteria we want to use, we then have to decide on a type of fragmentation. So there's two major ways to split our data up. One is horizontally, and one is vertically. Horizontally is basically taking a table and splitting up by rows. Splitting up by rows. So I've got a table, I'm going to take half the rows and send them over here. I'm going to take the other half of the rows and send them over here. So what do I have? I've got two locations that have one table that looks very similar to each other, right? The column names are all the same, the data types are all the same, the table name itself is probably all the same, but the only difference is the actual data contained. The number, the rows, maybe even the number of rows is different, doesn't have to be 50-50, right? Choose some criteria, maybe like location. All the data that's related to Chicago, I'm going to put over here. All the data that's related to New York, I'm going to put over here. I can also split things up vertically. So I'm going to break things up by columns. I'm going to take some of the columns, I'm going to put them over here. I'm going to take other columns, I'm going to put them over here. How do I get the original tuples back? If I take a tuple and I split it into two pieces and I store those pieces in separate locations, how do I get them back? How do I fuse them back together? What do I need? Yeah. You need the primary key. So if I decide to use vertical fragmentation, the primary key is going to be stored in all of the spots, all of the locations, because that's the glue that holds it all together. That's the glue that keeps it, makes it so I can reconcile that data. So this might be a case where we break something up by type, like we were talking about, the type of information, like we were talking about earlier. If I'm making products, information like the materials that it's made out of, right? How long it takes to make things like that. Those manufacturing related details might be kept in a manufacturing database. Information like how much I intend to sell that product for, things like that. Related to the sales side of things might be kept in a separate location related to the sales of that particular object, those particular products. The primary key would be in both spots, though, because if I ever need to get that information back into its original state, I need that information. Is that clear, the difference between horizontal and vertical? So then, now that we've talked about those two concepts, we can talk about how we can specify these different types of fragmentation. We actually use relational operations. If I want to tell you what tuples are belonging to the different horizontal fragments by rows, what select operation does that sound like? Or did I just say the answer? I don't know. What relational operation does it sound like if I'm trying to split relations up by rows? It's a select. It's a relational select, yeah. My brain is not fully functioning right now, sorry. Or maybe it's functioning too well. I don't know. Probably not, though. What about if I'm doing vertical fragmentation? I'm deciding what columns need to go where. What relational operation does that sound like? That's a projection. That's a projection. This is a nice, easy, concise way of talking about how fragmentation is set up. In fact, if I'm implementing this, if I'm actually doing this on a database, I'll just write it as a query. Here's the query that selects the pieces that I want to go in this fragment. Here's the query that picks out the pieces of this table that I want to go to this fragment, right? Because if I have a query, I actually, so here's kind of the putting it all together. I can use both at the same time. I can have horizontal and vertical fragmentation at the same time if I want to, on the same table if I want to. By writing a simple query, SQL query, I can specify the vertical partitioning by specifying what columns I want, and the vertical partitioning by tacking the horizontal partitioning by tacking a where clause on there. If I don't need one or the other, then I'll just write the query accordingly. Okay? So along with fragmentation is the idea of replication and allocation. Replication is what we use to improve availability and actually also autonomy along those lines as well. How does this improve availability again? I think I talked about this earlier, but little mini review. How does replication improve availability? Yeah. Yeah, if I have multiple copies and one of my copies is gone for whatever reason, the server crashes or the network goes down or whatever the case may be, I still have another copy. The data is still available, so it protects me from having that data go down. So replication improves availability, which kind of makes it seem like we should really enjoy that idea, and maybe go so far as to say, I'm just going to take my database and just copy all of it. I'm just going to make copies of all of it. What's the downside of that approach? Space. So I'm now using space. It's not just space, though. Consistency as well. Consistency as well. Those are the prices that I'm paying for that replication. So we don't want to go overboard. Are replications useful? Yes. Are they going to help? Yes. They do help with certain things. Absolutely, 100%. They also make some things difficult, more difficult. So if you can get away with not replicating stuff, that's actually a pretty good thing. There are the risks involved with that. The risks to availability, the risks to recoverability. If I lose that data altogether, right? I don't have a backup copy anymore. It's just gone, right? So there are some risks to that. But in the general case, how many copies do we want? Usually, if we are going to make copies of a piece of data, it's going to be relatively small. 2, maybe 3 replicas of a piece of data is considered plenty. Plenty, plenty, plenty. We don't often need more than that to satisfy our availability and recoverability needs. This can be used in conjunction with fragmentation as well. So fragmentation does not imply replication. They're two distinctly separate topics. I can use fragmentation, I can use replication, I can use both. can use both if I want to. I can decide that I want to make 2 fragments of this table and replicate one of those fragments, but not the other one. Or I can replicate both of them. That's okay. That's all right. I can mix and match however I see fit. All right? And so then that leads us to examples like this, where when talking about a distributed database, we have to understand the fragmentation and the replication techniques that are in use and make those decisions if we are designing a database ourselves. So Site 1 is our headquarters. It's going to have access to everything, all of it. Site 2 is the home of department number 5, and it needs access to the employee and project information for department number 5. And then Site 3 is the home of department number 4, and it needs all the employee and project information for that particular department. What kind of fragmentation am I talking about if I say that I'm going to take all the department 5 data, put it over here, and all the department 4 data and put it over here? What kind of fragmentation is that as it relates to the employees table, for example? Got an employees table? Horizontal, right? Got an employees table. I'm going to look and see the department number for those employees. If it's 5, it's going to go over here. If it's 4, it's going to go over here. If it's 3, it's just going to be at the headquarters as far as this example is concerned, right? It'll only be at headquarters. Is there any replication going on here? Yeah, absolutely. The data for Department 5 and Department 4 is being replicated. By making those fragments, I'm taking the data from headquarters and making a copy of it and putting it in a separate spot. So I don't have only fragmentation. I have fragmentation in conjunction with replication. Horizontal fragmentation in conjunction with replication. What should we do if there's a case where an employee from Department 5 works on a project that's owned by Department 4? What should we do then? How can our system accommodate that situation? We want all of the project info for Department 4 to be in one place. We want all the employee info for Department 5 to be in one place. What if there's some cross between the two? What then? Where does it go? Does it go to Department 5? Does it go to Department 4? Does it go to both? Could I put the employee in both spots? Is that okay? Sure. Yeah, there's no reason why not. Absolutely. That's more replication now, right? That's even more replication. I could put the project in both spots as well if I wanted to. Or if I really wanted to, I can make a decision and say, well, I care more about the project information being in the right place than the employee information being in the right place. So I'll copy the project to the other spot, but I'm not going to worry about copying that extra employee over. If I need that information, I can just go over to the other site and get it, or I can go back to headquarters and get it if I need to, right? Those are all things that we can say, and which one is correct depends on what your priorities are, what your needs are, what your requirements are for the database. Maybe space is really tight, and I want to avoid replication if it's not 100% necessary. Maybe I've got space out the wazoo and I don't care about replicas and I'll just copy everything because it makes things faster and easier for me, perhaps, right? Those are all things that we can take into account. Let's talk about Cori processing. So now that I've got data in different locations and maybe even replicas of data, right, it really changes the way that we approach our queries. First thing that I'm going to do when I receive a query is I need to map it. I need to map that query out. So what data is this query trying to access? We'll then do what's called localization, which is determining where that data is. So determine the local sites where that data lives. And then we'll perform a global optimization here. And so the question, what are we optimizing here? That's actually sort of the main takeaway from this slide. Because I've got data in different places, right? I'm optimizing communication. Or more specifically, I'm optimizing how much information I have to send across the network. The more data I have to send, the longer it's going to take. So I'm trying to minimize how much data needs to be sent. So I'm going to optimize this globally. I know where the data is. We're actually going to do an exercise on the very next slide to do this. I know where the data lives. I can compute how to operate this query using as little network transmission as possible. And then once I've determined that, I'll break the query into chunks, send those chunks off to the local sites, and they will do the local optimization, which is exactly how we saw it in the previous topic using the optimization heuristic. So let's look at an example of this, how we might globally optimize something. Here are a couple of tables. I've got an employees table, and I've got a department table. And it shows the number of records that exist in each, and it also gives us information about how big some of these fields are in bytes. Down here at the bottom is the query that I want to execute. So I want to grab the first name, the last name, the department name from employees, join departments. Okay? What I haven't told you yet is where this query is coming from. So I have these two sites here. One has the employees table, one has the departments table. I'm submitting the query at a third location. So I've got 3 locations here in total, site 1 and site 2 that contain my actual data, and site 3, which is just somewhere else. Now I want to know, all right, if I want to execute this query, what's the fastest way for me to do it in terms of data transfer? We actually have 3 options here. Because there's a join involved, we have 3 options here. I can grab both tables, both the employees and the departments table, ship them to the third site, and perform the join there. I can transfer the employee table to site 2, perform the join there, and then transfer the result back. Or I can do the opposite. I can transfer the department table to site 1, perform the join there, and then send the results back to site 3. Do those options make sense? Why there's 3 different ways we can do this? It's all about where I perform the join. Where does that join take place? Let's see if I can sketch this out. Actually, this is the wrong slide to put up on the screen for this problem. Let me go back and grab the other one. Really? Go away. All right, I got you. Sorry, one second. Please click the right thing. There we go. All right. So let's draw a little topology, right? Just so we're clear on what the issue is, or how this problem is being set up. Here is what my distributed database looks like in this situation. I've got site 1, which has the employees table. I'll annotate that down here. Site 2, which has the department table, right? And then site 3 is where the query comes in. So here's the query. The query that I'm executing is this guy down here at the bottom. Comes in site 3, and now I have to decide, oh man, that's way too small for you guys to see. Sorry, I'll fix that. Now I have to decide how to execute this query by sending as little amount of data over the network as possible. So am I going to do the join at site 1? Am I going to do this join at site 2? Or am I going to do this join at site 3? That's the question that we have to ask ourselves. So let's do some math. I'm going to erase this step. Let's do some math. And I'll zoom in on this so we can actually see it, hopefully. Okay. If I'm going to do the join at site 1, what does that mean? That means I'm going to take the departments table, I'm going to send it over to site 1. So how much data is that? It says there's 100 records. Each record is 35 bytes long. So the math on that is pretty straightforward. It's 30 bytes. Okay? I perform the join. And then I have to think about how much data I'm going to send back to site 3. So the columns that I'm keeping are the first name, the last name, and the department name. So first name is 15 bytes, last name is 15 bytes, department name is 10 bytes. So every tuple is going to be 40 bytes. And then how many tuples do I have? That was on the next slide. Oh, wait, it's not on the next slide. Sorry. Each record is 40 bytes long. Okay. Whoops. We'll just have to reason about it. How many tuples do I have left? We can figure this out. What's the type of relationship between employee and department? Many to many? Oh, many to one, yeah. Which side's the one and which side is the many? One department can have many employees, yeah. One department can have many employees. So that means that which statement is true? Every department must have employees, or every employee must have a department? Every employee must have a department, right? So then how many rows would I expect if I join these two tables together? How many rows would I expect in the result? I'd have 10,000. I have one per employee. I have one per employee. I expect every employee to have a department. I would expect 10,000 records in the result. So the size of the join data is going to be 40,000. 40,000. So the total amount of data for site 1, if I do the join on site 1, would be 43,500. Did I leave a 0 off? Yeah, sorry. 400. My bad. The commas, you know, it's just a comma. Yes? Do we need to send the whole site 1 table to site 2? Actually, that's a good question. We could ask the opposite question too. Do we need to send the whole site 2 table to site 1? We need the last name, first name, and that's right. In this case, though, we sent site 2 to site 1. So what do we need from the department table? We need the department number and the department name, right? So department number is 4 bytes, department name is 10 bytes. So instead of 3,500, we could say 1,400 here. Does that math check out? Yeah. We don't need to send the whole table. We only need to send the also be 1,400. So here is our final result. This is for site 1. So if I do the join on site 1, I'm saying it's going to take 400 and 1,400 bytes, right? All right. So site 1 was 400,000. All right, site 2. I'm going to take the pieces that I need from the employee table, send them over to site 2, perform the join, and then see how much that's going to be. So the only columns I need from the employee table, you just said, were the department number, the first name and the last name, correct? So department number is 4 bytes. First name is 15. Last name is 15. So that's 34 bytes. Correct? 34 bytes times 10,000 records. So that would be 340,000. That's just to send all of the relevant employee data to Site 2, correct? 340,000. I perform the join. The result of the join is actually going to be the same as it was last time, right? For, what was it, 400,000, what was it? Shouldn't have erased it. There were 40 bytes per record times, it's just 400,000, isn't it? So the result for this one is 740,000. Join on Site 2, correct? All right. One more time. Delayed reaction here on my. Site 2, we said was going to be 740,000. All right, both tables. I send them to Site 3, and I perform the join there. We've actually already computed all the terms that we need, right? To send the employees table over, that's what we just computed. It was 340,000, correct? So 340,000. Send the table over, we computed that earlier. It was 1,400, I believe. So that would be 341,000. And to me, that looks like the clear winner. 3, 4, 1, 4. Not by a huge factor, but still definitely better than the other two. So the right thing to do in this case would be to perform the join at Site 3. Yes?
Isn't that a little bit unfair because for site, if you're assuming that for 40 bytes per tuple when you're sending like a combined result, but and so the end result has to be 40,000, but the end result of the join has to be 40,000 bytes. It's like when you're sending 340,000, say you have to reformat data, stuff like that, so you make 40 bytes per tuple. It just seems like it's not really that like the amount of bytes that you're sending, because like the data going, if you're sending just the relevant field from Site 1 to Site 3, then you can have to reformat the data.
I'm not sure I follow. Performing a join is going to behave the same regardless of where it occurs, right? That's just a relational algebra operation. So the join itself, I would expect to take the same amount of time regardless of where I performed it. Maybe if the hardware is different, but if all the sites have the same hardware capabilities, I would expect the join itself to take the same amount of time.
So you're moving the data more times once it's on Site 3.
Moving it more times? I'm not sure that's the case. I mean, Site 3 is the destination. Site 3 is where the request came in. Site 3 is where the results need to go out, right? So there's going to be two movements of data no matter what. Whether I perform the join on any of the locations, there's always going to be 2 data transfers that take place. The last one will always be a Site 3 because that's where the data needs to end up at. There are definitely factors that we're not taking into account here, for sure. This example is strictly interested in minimizing the amount of bytes sent over the network. That's it. Nothing more, nothing less. If you want to talk about things like how busy the servers are, how loaded they are, right? Things like that. Or maybe not all network connections are created equally, right? Maybe server 1 and server 2 are very close together, and server 3 is very far away from them. We haven't taken that into account at all, right? That could have an effect on the results of these computations. This example, all it does is minimize the number of, all we're looking at now is minimizing the number of bytes being sent over the network. Yes?
Can you explain sending to site 2 again? Why are we multiplying the 40 by 10,000?
There will be 10,000 records in the results of the join. I expect every employee to have a department. So if I think about the what the result set looks like, it's going to be one row for each employee, and we said that one row is 40 bytes, so I get 400,000. In fact, these computations are all just slight reorderings of the same numbers, right? How much does it cost to send table 1? How much does it cost to send table 2? How much does it cost to send the joined results? And it is a simplification, right? I do want to make that very clear. We are simplifying this problem. We are definitely simplifying it. But this matters. To pretend that this doesn't matter would be leaving some potential performance on the table. Minimizing network traffic is going to be better for us. Absolutely. So let's try a couple variations on this. We have a few minutes left. This will be a good way to end today. Let's try a couple variations on this. What if I have a different query? So here we've got a different query, right? Now I'm asking for a slightly different join. How does that affect our data? And then, all right, in the previous examples, we assumed there was a third site. But what if that third site actually doesn't exist? What if we only have site 1 and site 2, right? And I just need to get the data to site 2 instead. How does that change the math? How does that change the way that these problems work out? Take a few minutes, think about these problems, do some math, and we'll talk about it. I feel like you're not satisfied.
So, you know they're going to have so you said 340,000, then after you do the joint, you're going to have to make mistakes. When you do something like send, well, there's still like no passport, then it's just going to take right? So like, when you send some site to study, you make one copy of the data, you send that straight away. But like you send the relative site, send the relative site to it. And you're going to have to really do that one. Seems like, that's not you're sending it. It's not like the same thing as you said. Yeah, you're sending so it is less now same result from you're gonna get the same result. Or you're gonna get dual computational. Saying, I want
Yeah. Yeah. So yeah. 4,000. I'm sorry? And then applying the same sort of so the next Okay, everybody, we are unfortunately out of time, but we'll start next time by talking about these problems. And actually, I want to give you a heads up that next class, Wednesday's class, has a lot of practice problems on it. A lot of in-class stuff for you guys to do on Wednesday. Great prep for the final exam. So please come on Wednesday. Please come ready to work on some practice problems. I'll see you then.